Good, thank you. So this is going to be about consensus in blockchains, yeah, and the overview of this. So you should, in the room, or I'm not sure if out of the room you can ask questions, but definitely if you're in the room, you can ask questions also. The plan is going to be like this, yeah, starting with an overview of a couple of different models for consensus in blockchains. How this is purely subjective, how I see those models have to come. But it's about the influence, how people influence the consensus in blockchains. And then we can go through a couple of results that are in this model. Each result will be about one particular model, in one particular model. Each result will exploit one model. And we can ask questions along as we go, of course. Now, the oldest model that has been used in distributed computing is the so-called voting model that we call sometimes also threshold trust. Threshold trust means we just count votes. Every vote counts the same. And when a majority of the nodes decides to do something, then that's what the decision is. And that means also in the counterpart, we can overrule some others, and who we overrule in this picture here, shown here, is so-called, well, we have a supermajority that more than 2/3 we need to be correct here, so that the assumptions of the system are maintained. And so we can tolerate in this picture only less than 1/3 to be faulty. And in this picture, we're just voting. Many works in distributed computing have used this model in the past. They have started, so there's decades of literature on this. There's this little textbook here that I can also recommend for you to get an impression on how some of these protocols work, but they are only working with the protocols where we vote. So what the majority votes is what is done in those systems. Why it needs to be more than 3F? For this, you have to look into this theory, because it has to do with nodes that can be slow, and we don't want to wait for the slow nodes necessarily. So this is an assumption has been often made traditionally in distributed computing field, but blockchains have challenged this view. And now I'm going slightly to other assumptions that have been used also in distributed computing in the blockchain world. And one of them that has also come out of the distributed computing literature is so-called generalized trust. Generalized means that not everybody has the same influence. Like we have some fat node here with a lot of influence in certain way, but which is still possibly faulty here. So we are prepared to tolerate these two that are faulty. Yeah? We can formalize this using notion of so-called fail-prone sets. We are a priori going to define which combinations of nodes we want to tolerate. In the previous picture, this was just any minority that we wanted to tolerate. Like any two could deviate. Now it's not only any two; it's maybe this two, but among the smaller ones could be 3, or we could say there are different classes of nodes. Some are more trusted than others, so the ones that are more trusted are less likely to fail and to disrupt the system. This model here is, as I call it, heterogeneous, yeah, because not all the failures are of the same type, we would say, yeah, but it's symmetric in the sense that every node that participates in this consensus system, in this distributed system to reach, to push the blockchain or the cryptocurrency forward, all the nodes adhere to this assumption. They all believe that these guys are maybe faulty or those two are faulty, so they all adhere to this. Yeah.
Can you come closer to the mic?
I should come closer now. Then I'm going to sit in front here probably, because otherwise I'm standing in front of the, if that's fine. Yeah, yeah, okay. But then I can draw on it. That's also good, right? So before we had seen that there has to be the number of nodes bigger than 3 times the number of nodes that we tolerated to be faulty, right? We had this condition n bigger than 3f, right? It's not only a majority like we need in democracy, like a quorum. This is like a so-called Byzantine quorum, where we have a majority that has to be 2/3. And here we are going to define who can fail. and we defined a set of possible faulty nodes, and no three of those possibly faulty node sets must cover the space of our all system. That's this generalization of the n bigger than 3 condition. Yeah, this model is actually not used by any blockchain. I wanted to mention. Yeah, interestingly, there is a generalization of this where now we no longer have this symmetric assumption, but every node is free to make its own subjective choice like this. So you see here in the picture, there are only for 3 of them I have shown the analysis, but there is the one with the grid pattern, there is the checkered one, the one with the full nodes. These are 3 nodes that each express whom they trust how much. Yeah. So each node in this model that we call asymmetric, it has been, each node can express now how much they want to tolerate failures, which one they want to tolerate. So this is, in the first place, heterogeneous, because not all dots have the same diameter as all, but it's also not symmetric, because each node can have their own trust assumption. It may also be the case that not each node knows all the same other neighbors, and those who trust, those who you trust more. And there's a further generalization of this, which I'm not going to go into now, that asks the so-called B3 property that in this model will determine whether from such a set of assumptions a priori we can get the so-called blockchain consensus, which is what we all want. Yeah, this is something that was introduced. These models were introduced first in the blockchain world, namely by Ripple, and then later by Stellar, that formalized models like this. Not exactly this one here, but model like this. Yeah. And so these are models that we have seen so far that are based on votes, where the power of influencing the consensus protocol comes from this a priori agreement, or maybe less agreement in this picture, of how much they want to influence. Any questions so far? Not really? Okay. Yes?
When you say power of votes, you kind of assume no synchrony, we cannot leverage any of this.
Okay, I was working in an asynchronous model. That's why you saw the n bigger than 3f before. That's why also you see here this what I call B3. But this can be transported into the synchronous model. Then we need a majority or a B2 or a Q2 condition, or yeah. So this is for the model where we don't have synchrony for safety, I would say. Yeah. But in the other models, I am flexible with this assumption, yeah, because the other models that we just see, they are usually often needing some timing assumptions. Yeah.
Sorry.
Yeah, go ahead.
In asynchrony, we don't have anything deterministic, right? So
in asynchrony, we don't have deterministic. Okay, well, there is more technically speaking. Now going back to this one here, yeah. More technically speaking, there's a model that we call eventually synchronous, where we can have deterministic protocols that are guaranteed only to make progress when the world is synchronous, but they are never violating their safety while the world is asynchronous.
No, I was curious, those B3
and this is the bound. This is the bound for that world. Yeah.
No, but B3 and Q3, are they deterministic bounds? Or
this is just in an abstract sense, yeah. But it models it is appropriate for the same type of setup, for the same type of protocols, right? So you can have, in fact, you could have randomized protocols that get around this deterministic impossibility. But this is maybe a corner case I don't want to talk about too much here. Yeah? Randomized protocols can make the likelihood of you not terminating infinitesimally small, and then you're fine again. In fact, in our paper, like in this paper, a successor, we have a randomized asynchronous asymmetric agreement protocol. This is asymmetric, right? Not and asynchronous. Okay, so this is voting. We have just assigned by votes based on, let's say, some external notion or assumptions about who may fail because we know something. Now there's a different model that has gained a lot of popularity in the blockchain world, and I'm not even talking yet about the blockchain model that started all of that, namely the Bitcoin model is proof of work that will come, trust me. In this model, we break up this structure
what I call unstructured voting is an attempt to be more faster, because we are not bound to these overlapping quorum sets in a certain way. And we are saying, oh, well, we just sample a random subset of nodes, for example, in one of the protocols, and then we adopt the opinion that they have. So maybe they get a consensus through this, yeah? Typically, they are exchanging the information they know. The protocols are less structured, and interestingly, these protocols, they also construct the so-called graph, an acyclic graph of transactions, yeah? Why this is, I can't say, but I've just observed that this is typically a feature of those protocols. We will talk later about the Avalanche protocol. That's an example of this type of family of protocols where you just sample nodes and you ask them for your opinion, then maybe if enough of them say, you're adopting it as well. Then there are the protocols that have to do with stake. Stake is now investment in a certain way, where you are, in traditional world, shareholders of a company. Then not every shareholder has the same number of votes. Namely, your votes are strictly proportional to the amount of shares you hold. And in the cryptocurrency world, this idea has gained a lot of traction because it allows you to get rid of this proof of work that will come later, and that is a waste of energy in a certain way. And it reflects the economic reality of who is invested how much into this chain. And in this protocol that I am showing here in this consensus model, the stake alone will determine your voting power. So the circles have, again, different sizes, but they're strictly proportional to your holdings in tokens of this blockchain. So if you hold many, you have more power. So oligarchy, if you have a lot of tokens, you have more power. If you hold few, you have nothing to say, yeah? This is a line of protocols that can use basically the original protocols from the textbooks. It's just that we replace counting of votes by this counting of shares or tokens in a certain way. But this is not the only type of protocol that we can run with stake.
You don't include Ethereum in this list?
No, not yet,
oh.
Because it's stake-based voting, okay? It's just based on the voting protocols when we generalize the protocols from here. Because here comes other protocols that use different characteristics, yeah? I'm looking already at the implementation, not just at the assumption. Ethereum uses, on top of this, other assumptions, the current Ethereum. Namely, it uses, not in this one yet. No, it's not yet this one. Okay, so we'll come even one later, okay? There are other protocols where there is no voting happening based on the stake, but the protocols where a so-called leader is chosen proportionally by some randomness shown in the middle here. The leader is just chosen by some maybe cryptographic magic, that's sitting here, where the cryptographic magic makes somebody a leader, power of their holdings and of stake. And with more stake, you're more likely to be a leader for a certain time. And when you're leader, you can impose your wish. Yeah, you cannot do whatever you want, but while you're the leader, you can actually exert power, and you can extend this chain and write the ledger further, write the book further. The Ouroboros protocol that's in Cardano is maybe the most representative sample of this family of protocols, yeah, where there's just randomness. Yeah, there's also Algorand that has the VRF, but it adds more. Algorand adds more. Algorand is a hybrid, so these are all protocols that are on CoinMarketCap. They have all billions invested in some sense, and many of them have some academic pedigree and academic advisors that influence them in this or the other way. Yeah, so there is a hybrid between this probabilistic voting or selection, where you're just elected with this randomization power to be a leader, but not only that, then you have to do certain things correctly, and others will vote on whether you have done certain things correctly behind you, yeah? And I count Ethereum among this type of protocol here, where it's actually a family of two. You have this Ghost and the Casper, and one is maybe for running ahead and does not use the votes, and the other one is running slower behind you and using these approval quorums to approve what the fast protocol has decided or has run ahead. So in this case, we use the voting based on the stake. We use the randomization because also in this Ethereum protocol, or in the other protocols mentioned here, we have some common randomness or maybe some private randomness that is generated with, let's say, advanced cryptography. It's a mix. These protocols are getting more complicated. Yeah, it's not just a clean design, which probably means that they're practical. Okay, now there are even more protocols. Okay, there is a protocol here, a protocol family where we have to invest some resource, where we are going to prove that we have invested a resource that is of some kind. Maybe we have invested storage space and we can do something useful with the storage space. Maybe we can store other people's data. Filecoin and the proof of storage type of networks are of this kind. Also this StoreJ or the Kia network. In the Kia, you have to store things, but also prove you waited a certain amount of time. That's why the clock comes in here, because the clock or the temporal dimension here in these protocols means that you have stored something over a certain time. The idea in these protocols then is, again, you have a lot of voting power if you store a lot. So you have more influence if you store more, and you are less often there when you store less. And in this picture here, like always in these protocols, there's an economic incentive that I've glossed over so far. If you are helping run the protocol, you are paid in the token of this blockchain, and you're gaining through this as well. This is also an element that is crucial in those protocols. Yes?
The proof of space, proof of delay is orthogonal to the categories 5, 6, 7.
I'm lumping them into 8, right? Because the random selection with the stake has, when you look inside the protocols, clearly different characteristics. Yeah, I'm not sure if there is a protocol that uses the random. Well, the proof of space is another one, right? Because what comes now, what the 9th would be the proof of work in the Bitcoin, where you solve the random puzzles in the block, and the random puzzles or the arbitrary puzzles that are just made to invest a lot of so-called hashing power, and your combined investment is the one that will drive your, it will give you voting power. The more you invest in so-called mining work, the more likely you're winning there. And in that sense, you can see it as a separate mechanism, as a separate resource to have influence, namely the space. Yeah. Now, can protocols be exactly the same? That's a research question. There's not exactly the same protocols typically that we can run with proof of work as we can run with proof of space, but they are related. Yeah, and we have something to say on this also.
Well, I guess this is more like resource from outside the system versus proof of stake, resource coming directly from the state machine.
Yeah. And this relates to, it's mentioning a paper here that I'm going to mention later about how to unify a couple of different resources for blockchain consensus. And then there is the proof of work, which is what started blockchain in Bitcoin, that we are going to mine, sort of solve an uninteresting puzzle that is totally parallelizable and serves no better thing than actually keeping the chain secure. Okay, so these are a couple of models. If you have more questions about the models, now is the time, because that was the last one I wanted to end up with, not historically, but in this spectrum, okay? If not, then I want to go into the models again, not through all of them, but selectively show certain results that exploit or that we can actually only explain within a particular model, yeah? So go back to this model where we have votes, yeah, where we have a number of nodes and they're just voting. And now let's look at one interesting problem, which is the so-called MEV problem for the jargon, for those who know the jargon, and otherwise it's called the insider's fraud or front running, yeah. So in traditional financial markets, if you are in the trading floor, yeah, you can exploit information that others don't have. You see the trades come in. You see the wishes. I'm going to buy this much at that price, okay? Front running means that I would just exploit this knowledge and try to extract something from your trade, because I now know at which price you're going to buy, okay? I can make my price then, my selling price exactly this, and I will have a better profit from me if I would sell at what I think is the price. Now, this has to do a lot with information asymmetries that exist in traditional financial markets. Now, on the chains, where we talk about this so-called DeFi, somewhere it says DeFi, yes, here, decentralized finance, the idea is that the exchange, the stock exchange, runs on such a blockchain. Blockchain is run by a couple of validators. So the validators, before they execute collectively the transaction, they will have to know what things come in. So they will see, oh, a transaction come in. She's willing to buy at this rate. Okay, I can front run this transaction and extract value. This is being done currently on the Ethereum blockchain, even as a service. It's like everything that can be extracted is actually extracted like this today in many situations, because there is no such trusted entity. What one could do here is two things, namely break this causal chain between knowing my transaction and your ability to insert the transaction that front runs me, right? Put some encryption there. This is one of the solutions. And the other solution is what I'm going to talk about here is like a voting-based protocol. That's why it's coming in the first model. Voting-based means that my innocent transaction here, or maybe my couple of transactions from different clients, they are going to arrive at the validators. There are 3 validators here in this picture in different orders, okay? And it should be the case that if my transaction, say, arrives at many validators earlier than your transaction, okay, then it should also go into the chain before your transaction. Yes, and that was a question.
Yeah. Why can't you just have all the transactions in a block take effect atomically?
Why can't we just have all the, yeah, that's one of the solutions. Why can't we just have all the transactions in the block atomically take effect? However, that will stretch the notion of what goes into a block. And maybe I can put something in the block before and after, right? I can hold back your transaction to the next block, right?
Well, transactions might conflict.
Transactions might also conflict, right? And so I have to make sure they're also valid. But in a way, what it's already done, that we go through the transactions in the block and we sort out the ones that are not valid, right? But
that isn't the decide which one is valid, which one isn't valid, and you can make a profit.
yes, and because I form the block, right? Because I'm forming the block, that's my power, okay? So I want to take away the power of the block formator and make sure that they have to rely on the collective knowledge on the system here. These replicated nodes that will have seen, one of them will have seen it M prime before M double prime or before M3. The other one might have seen M3 before M1 and before M2 and so on. This is what we call the input order. So we want to make this choice depending on the input order. It should be more fair. This also is called fairness, right? Sort of transaction fairness. How can we get a fair order such that if my transaction was fast there, you can't just like see this and get to this power, okay? So this will require maybe some voting among these nodes. Did we see this first? Did we see that first? And so on. But turns out, and this is not our result, but this is from our Jules and a couple of colleagues, Mohim Nakelkar and others, you cannot always do that, because it could even be the case that these transactions, the preferences among many transactions form a cycle. Yeah, because it could, it's called the Condorcet cycle, because I prefer this before that, but you prefer the ones shifted by one, and you prefer, or you have received the ones again shifted by one. This is exactly what's shown in the picture. All these orders are sort of like circularly shifted, and in this case, we cannot really say what is better, what comes first. So this is recognizing this is doing what you said earlier in a certain way. The solution will be to put them all at the same sequence, right? To put them all in the same sequence and say, these transactions cannot depend on each other. They have to be done in the same height, basically, and we leave it to the application, or we reject all of them, because not, if they have some dependencies with each other, we cannot decide what should happen here. And we looked at this situation later and defined a slightly refined notion here that we called differential order fairness, where we count, and you can see here now counting for each pair of transactions. They're called M here and M prime. which one arrives first at honest validators before another. Yeah, if eventually everybody is going to receive an M and N prime, how many honest validators have received M before M prime, and how many have received N prime before M? Yeah, and some nodes are still corrupted. We can count the corrupted nodes, and we are requiring now that if there is a substantial difference between how many honest heard M before M prime and those who heard them in the reverse order, if this is bigger than 2f, then we can ask that they not show up in the reverse order. Then we cannot have M prime before M show up, yeah, because there was a majority that heard M before M prime. And why do we have this sort of threshold in there? Well, this goes back to resultant distributed computing, namely, if there is less difference, we cannot even decide. There's no protocol whatsoever that will decide in this case what should happen. Yeah? So that's a result here that in the references, you can read up all these theorems in detail later. And we have a protocol here. We call this the quick order fair atomic broadcast protocol because we thought it was faster than the previous protocol to do this. Yeah. Basically, the nodes exchange their information about in which order they received these respective transactions. And then if they can decide, they will put them in the corresponding order. If they cannot decide, they will do what's written here. They will just put them at the same thing and say, hey, okay, maybe they must be all rejected, or maybe they should not depend on each other. Questions? No. Let's go to something else then about the models. Who remembers this generalized trust model? That not all nodes have the same influence. So let's look at this now. For one thing, here's a picture like this, where we could say, in this picture here, we have 6 nodes, and there are sort of 2 groups, the upper group and the lower group, and any two of them might collude together against the rest, against the system. But any 2 of this group might also collude, but there is never the case that one of the PQR group colludes with one of the XYZ groups, yeah? And in this model here, we can actually run consensus protocols. We formulated them. This is not, but this is not something that we developed for the first time because this goes back 20 years. But we actually developed mechanisms to run these protocols. And going a step beyond, we're developing mechanisms to run sort of distributed cryptography with these tools. In this model here, we can also do distributed cryptography, like something called threshold cryptography. Yeah? I'm not going to talk much about this except for this part here. A lot of these systems where you hold the consensus power in a group of nodes, and F of them can be faulty. You can also do cryptography like decryption or a collective signing power, where nodes collectively sign with one key that belongs to the system. No single node knows the key, but it's held with a secret sharing in the jargon, and they do a so-called threshold crypto protocol to sign. Now we can take these threshold crypto protocols and generalize them to this model here, where it's no longer by the numbers, but by so-called access structure. Now here we can tolerate and say, for example, here, this is an example that we got from one of the blockchains that uses something like this, namely Stellar. They have something where they say here, 2 out of these 3 here are sufficient, or 2 out of these 3, or down here has to be 3 out of the 5 lobsters. And then we need 6 out of these, I don't know how many, maybe 8 of these groups who are consenting to do something, yeah? And we are doing the cryptographic operation in the same way, yeah? This is like implementing the stuff and running the crypto operation like this. This needs tools, right? This needs tools because we are going to take this config file, we translate it into a linear algebraic representation that's called a span program or a monotone span program. And then we do the crypto in this world, the distributed cryptography, we generate 1 signature or 1 decryption or 1 sort of unpredictable randomness, or we share 1 secret in the so-called technical protocol called verifiable secret sharing. And the goal of this work was to show or to find out how much slower is it than the regular distributed crypto. Yeah? So what do you guess? cryptographers. How much lower is it
What?
than threshold crypto with Shamir secret sharing? In
It's
the
regular.
yeah, like where
Same.
should be the same. It's not necessarily the same because we have a spam program now, and
Spam programs are pretty efficient.
they're pretty efficient. Yes, that's good, but they're not the same, right? But they're not exactly the same because it depends on how complex is your configuration structure at the bottom, right? And indeed here you can see some plots of results where we have sometimes a span program construction also used for something that we can also express as a threshold. So for example, if you look at the polynomial one here and the span program here, they're not exactly the same. Actually, no, this is wrong. This is wrong because the two lines are on top of each other. The two lines here are on top of each other. That's what you're saying. But here, they're not. Here, they're not. But they're pretty close, yeah? But we're also going up to 100 participants here. If you have more complex trust structures, like if your list of how complex it should be, then it gets slower here. Latency will vary a bit, will go up a bit, yeah? But not by too much, yeah? So because this is still efficient enough so that we claim it could be done in practice as well. So that was these results, doing it with more general trust, yeah?
Sorry, these results also include key generation, distributed key generation, or is there a trusted dealer?
There's VSS only. There's no key generation here, but there will be multiple.
This is not for signatures.
This is VSS.
Oh, this is for VSS.
Yeah, VSS is also, it's not key generation, but n of these VSSs plus some consensus will give you key generation as well. So it's not too much different, right? It's more implementation complexity, yeah? But the VSS is the most important building block for those types of protocols. And in the other things we have like randomness generation with a coin. That's a simple. So with the BLS coin is much simpler even than the VSS. Okay. Now we were at the generalized model, so let's go to the asymmetric trust model. Let me talk a bit about this also, how this would look like in the picture here, like repeating the assumption first and repeating that now it's asymmetric. The who fails would be different according to who you ask, yeah? So you ask node P, P says, I never fail, yeah? Because otherwise there's nothing more to say. But my neighbors, maybe I trust them a lot, so maybe they're never failing together, right? Maybe one of them is faulty, but then not the other, okay? And those who are further away from me, those that I don't know so well, those three above, maybe any two of the three could fail jointly together and collude against me. And so this gives you this so-called failure specification in a more detailed way that we could call a fail-prone system. And in this model here, the nodes will trust differently. That's in a way the same model that is underlying Stellar, except that formalization here is different. And with this, we can do the standard protocols from the textbook, and I'm going to show you how this works here. So, oh no, not yet. Well, first I want to motivate it once more why this makes sense that you trust differently from him, right? First of all, there's no such thing like arguing about taste, yeah? You cannot really, you like this, you don't like this. Like some people like something, others don't like, you cannot argue about this, yeah? There's a Roman way of saying this, right? Yeah, that is, okay, that's it, right? Yeah. When you go to computer security conferences, also when you probably are in a company and people argue about, security officers argue about which attacks are realistic, they're hugely different in a certain way because it's difficult to measure what an attack does. So they can argue forever why this is a realistic assumption or not. So again, right? But in the blockchain worlds, the Ripple and the Stellar chains that I mentioned here have introduced this idea, and that's why we're also looking into this model, what one can do and what one can say about these quorums. And what I want to say here is not too much, except that when one then looks at these systems, we can have a new kind of nodes. In the particular models in the past, there were nodes that were either correct and they were good. Everything was good for them, as long as the fault assumption on the whole system was satisfied, as long as like you had a minority or less than 1/3 of the nodes that were faulty, And you have all the other nodes that are faulty, and we don't guarantee anything for them. In this model here, now you can have nodes that are correct, but have the wrong friends. They've made the wrong trust choices, yeah? So we go into some execution of the system, and there are these correct nodes, and they are getting frauded, or they're being cheated in a certain way. They think they are not consistent with the others, because even though they are correct, their guarantees are not satisfied. There may be others who we call wise. These are the naive nodes because they have made the wrong choices. There may be others, and they are called wise, and the others have made the right choices. So they will be given the guarantees that the system has. And then when you go more detailed into the protocols, we're not going to do that here. We are going to rely on a set of such wise nodes that is also closed in a way that they have the power to make decisions, and it's what we call a guild. Yeah, that's too much for this moment here. So let's not go into this. But what we want to ensure here is, now this is a picture from, say, one of those textbooks, where previously in the standard protocols we have basically a step in the protocol, in the counting based on the threshold protocols, that says, let us receive votes from n plus f over 2, like we defined n nodes and f of them are faulty, and then we can do an action like do something here in the protocol, and we want to replace this now just in the protocol by these processes, by these quorums. This process here has a quorum for itself, any node, any set of nodes that convince this node W, and another node here, which is a reader in this example here, is convinced by a potentially different quorum, but if they are both wise, then they are consistent with each other. Yeah? If one of them would be naive, then we are not guaranteeing anything to this node. So that's the idea of this research, and we have a couple of papers exploiting these ideas as well.
So
Yes.
I know what SMR is. What is SWMR?
That's a different jargon. Okay, this is about a abstraction of a storage space that we call a register. Has nothing to do with SMR. A single writer multi-reader register. So this is a register with regular semantics for which it's clear who has the power to write and for which many different readers can exist. Yeah. All these things mean something about semantics of concurrent interaction with the storage. You can think that you write something to the cloud, and the cloud is implemented in a replicated system, and you are going to retrieve something like this. Those mechanisms are actually at the core of consensus protocols like PBFD or Paxos or these type of things, because you're in a certain way, you're also locking values in there, and you're reading what has been locked by an earlier. So this is at the core of those things. It's just a very, very simple example. Yeah. But it's a good question. Okay, then let's go to the probabilistic and unstructured voting consensus. And now we can return to the protocol I mentioned before that has been called Avalanche. Yeah, and I guess we did the first independent analysis of the Avalanche protocol, because this was a protocol that had been proposed in a preprint paper, and then it has been implemented. It's one of the top 10 nowadays as well, and it relies only on this notion of sampling a few other nodes about what they think about particular transactions. So it's based on random samples and these transactions. The idea underneath is sort of easy to understand in a way that we say, let's say we can only decide red or blue, and then I'm going to ask a few people randomly whether they prefer red or blue, and if a majority says red, I'm going to switch my opinion to red. And based on the randomness of the sampling, we should be able to get around this fact that we can continue in a sort of bivalent state forever, right? The question is just how fast can we go on one side or the other, right? It was called Avalanche because of the idea that one little snowball is going to grow into a bigger snowball as it grows and goes down some slope. Yeah, and there's a couple of there's a slush, there's a snowball, a snowflake, and there's a family of protocols. Okay.
There's actually a website, online website, that you can see a simulation of what's happening in real time.
Oh, a simulation with an adversary inside. or not. But that's so. What's not advertised on the Avalanche website that widely is that where we have seen the corruption bound before, that was like we can tolerate the number of corrupted nodes has to be or can be up to n over 3. In these types of protocols, we can only tolerate many fewer nodes to be corrupted, right? So square root, or let's put the big O here for those who speak the jargon. So it's actually not that many that we can tolerate, but still it's an interesting question, right? Because one in these protocols often, and this also happens here, you have to make some kind of investment, and if you provably, demonstrably misbehave, your investment is gone. It's called slashed, yeah? It's taken away, right? That could deter even square root of n of the attackers from attacking it. Yeah. Anyway, what happens here is also that the transactions building a DAG. It's not only blue and red, but on top of this, we are building a DAG of transactions. And now the question is, are no longer so independent of each other, because some transactions, the transaction here refers to earlier transactions, this refers to even earlier transactions, and so on. The beauty of this graph here, this relation graph, this DAG, is that we don't have to totally order all transactions with respect to each other, right? It may be the case that T2 here and T3 here came up at the same time and they are not conflicting. In this case, we can make both of them go into this ledger, and we don't even have to say which one comes first. And that's one of the things that also makes it faster, okay? Avalanche. And all the protocols that do stacks in this sense. And that's why it's also been used a lot. That gives us this property here, that we don't even have to say in which order they are accepted. On the other hand, it's also creating potential for conflicts, because when you output a transaction and you output another transaction, you may lead to a conflict that because you didn't know of what was the current state, the two transactions might conflict, or might even be both from you. And what happens then? What happens then? Well, let's just see. I can't go really into the details of this here, but here is how the protocol, the Avalanche protocol, aims at resolving these problems. Basically, we see here what happens, that we pick a random transaction in my pool of transactions that I'm not yet sure whether they're going to be accepted. I ask these random nodes what they think about the transaction, and they are going to be sending me ups or downs, whether they like the transaction or not. And then I'm counting, okay? I'm counting how many times other people have said yes to this transaction and how many times others have said no. And if I go above some threshold with this, I'm going, say I'm asking about this one here, yeah? Then I'm keeping a little counter for each transaction in the past here, in this causal past. You know, they point to other transactions that preceded in this way, that are before. If this, I increment the counter for all those in the past. And if this counter exceeds another threshold here, this beta threshold, then I'm going to accept the transaction in the past. It could be, though, that this transaction in the past, I'm already knowing that it's part of a so-called conflict set, like the two blue ones, okay? Now, the two blue ones now, suppose they're conflicting with each other, okay? In this case, I need a higher count. I need a higher counter value to be surpassed so that they can still be accepted. That now introduces some complications also, because when, say, there is another transaction out here that will refer this one here and this one, it could be the case that, oh, I haven't said yet what happens here. Yeah. If I don't get enough positive results, apparently my transaction could be wrong, okay? So I'm going to reset this counter again. I'm going to go back to the history here and reset that counters to 0, as it's written here, yeah? I'm going to reset these counters to 0, so I can cause something into the past. That now is no longer this independent blue and red voting that happens on the transactions, but now they depend on each other. And as we show in this paper, there can indeed be a problem with this, namely with one such extra transaction and putting this into sending this transaction to the right honest nodes at the right times. I can delay a transaction like this from being accepted forever. Yes, yes. Turns out that we did this research. We go to the protocol and we see the protocol doesn't actually do it like this because our attempt to show the attack did not succeed. So we talked to the Avalanche developers, okay? And they say, oh, we know about this. We have some fix, like patch, yeah? And it works not exactly in the way that I described because this was a mix of what they wrote in the white paper and what they also had in some parts of the code, but not just the full code, okay? So it turns out that this DAG protocol that can accept transactions concurrently was actually also deprecated soon after we did that for other reasons, yeah? The other reasons were actually very much more mundane. You have an idea why? The reasons why they retired the protocol. Apparently, it's not only the fact that it doesn't come with a clean analysis like that, but much more that we heard that for an exchange, you want to have a total order on which transaction goes in first, yeah? And you have this DAG that some transactions were not ordered with respect to each other. The exchanges where people go from the coins to the real money or the other way around, the exchanges were not able to deal with this in a clean way, yeah? So that introduced too many complications. So as of today, Avalanche is not using this DAG protocol anymore. They're using another protocol again. We're looking at those other protocols now again. Okay. Yes.
So in this DAG protocol, I forget, is there a notion of finality or not?
Yes. At one time you accept. Here.
No, you accept, but how does the rest of the world know that this transaction is finalized?
Well, the rest of the world can ask a couple of nodes whether they think it's finalized. And then how else are you going to know a transaction is finalized?
Yeah, I guess.
You ask a couple of nodes, and then if you hear only this is, yeah?
Yeah.
I mean, if you know from the system that they have quorum, and you have a majority or a 2/3 majority say this is, yeah, if you know how they do it, okay? Here, is this not right anymore? Okay, I don't know. Here, it's not so easy, yeah? You have to talk, but the number of nodes that can be corrupted is much smaller. So if you ask a linear fraction of them, you're going to be fine, okay? And in order to be a first-class validator on this network, I think you also have to make an investment of several 10K. So then the set of nodes, the N here is not huge, yeah? Okay, so. One more.
Not huge. Do you have an idea how small?
N is not huge, hundreds.
How much is square root of n in money?
I did not do this calculation, okay? We did not want to go to the ethics board before doing things. Right? We talked to developers though.
In practice, do we, how do they sample? So they sample not from the entire universe of validators.
No. In order to be a validator, you have to make an investment, and then you're a validator. But I don't know how many there actually are.
Yeah. But what I'm saying is that do they have a subset from which they sample, or do they sample from the whole universe?
I believe they sample from all of those that have made the investment so they become slashable. So we did pretty much everyone who makes several 10,000 investment. Yeah, it depends on the price of the token, of course. Yeah. Okay, one more thing. So the Nakamoto protocol, the blockchain protocol that sits at the beginning of all this, uses this longest chain. Okay. And I'm starting abstractly for those who already know. I'm showing the example in a moment. Because the blocks are going to be put so that each block points to a predecessor, and you're going to get a tree, okay, when you produce blocks. And the Nakamoto rule is to accept the branch in the tree that is the deepest, the longest, right? The longest chain. So let me just show it nevertheless, okay, which will be in this picture here. We have a genesis block at the top, and this is the longest fork here that is 7 blocks deep, where Nakamoto protocol would accept this one. However, if you are now trying to make the protocol faster, Then there will be blocks that are produced at the same time, roughly like this here. And this is why, let me go back here now. Early on already, 2013 or so, a rule called ghost has been proposed that would select the blocks differently. Yeah? This ghost rule would select blocks according to the heaviest subtree that you can observe from a moment where you sit in this tree. And the idea is to give credit or to rely on security that has gone in this investment of mining power into the blocks that are sitting just outside this main chain, outside the longest fork, the longest branch. This is the ghost rule, and has been proposed and has been adopted, also used for some kind of variant of it in Ethereum. And we were wondering here how they are different, how are these nodes, how these rules are different. Is there a way to find sort of a family of chain selection rules that bridges them? That's why it's called a bridge, right? Now we found it, it's called medium. So let me explain here again. These are the trees that can be produced. Suppose this is an execution that starts like this. The Bitcoin rule, the Nakamoto rule, would have selected this longest chain, okay? Because it's the deepest, okay? In practice, this is very conservative because between the production of one and the next block, there are 10 minutes, right? If you try to make this faster, and for a while people try to make the chains faster, just because they are, by reducing this time here, you're going to more often see stuff like this here, where they fork or where they even fork broadly, yeah? And the ghost rule now was introduced to select, in this picture here, the middle branch of this tree, namely the one that is the heaviest. Now it's called ghost for greedy. So you go here, you select the heaviest subtree, the subtree with the most nodes inside from the point of view where you are. So you're going to select this one, and then you're going to go here because there are more nodes. Oh, the count is no more here, but I think there are 10 nodes in this subtree from the Genesis and only 9 in the left. Yeah. On the other hand, if you look at this tree, you can also realize that an adversary that has gained some power could have produced blocks deep down in the tree in the past in some place, right? This is something that has been held against Ghost because it actually allows sort of post-factum corruption like a long time after if this investing mining power changes over time. And so that's why it's not so popular, right? And so what comes in here now is that rule that we formulated to bridge between the two. We just put a weight to the blocks, depending on how far they are from the genesis, from the fork. And we weight, so we count them by an exponential in the distance from the genesis. If you're at depth d, we count them by some constant c to the power of d. And so we're going to count the total weight is going to be a polynomial in this d, in the depth. Every node counts towards this. If we set the constant c here to 1, then we count number of nodes simply, yeah? And the number of nodes counting is what the ghost rule would give. And if we set this constant to arbitrarily large, to infinity here, then we get the Nakamoto rule. So indeed, we have now a parameter we can tune between the ghost and the Nakamoto rule. And if we set it to 2, then in this case, of course, I've picked the example already, we would select the leftmost branch of this tree here, which for some people arguably looks more like more mining power had gone into that than the other. Yeah? So this is a result about this type of protocols here. Yeah? Question? No.
So what's the impact? What do you mean? So what's the impact of this on long-range attacks? So what should you choose C if you're worried about long-range attacks?
We haven't evaluated this. We have not evaluated this. The long-range attacks actually are not possible in this picture in our analysis, because the long-range attacks come in when the mining, when some keys that were used up here are exposed, right? So when something in the environment changes that we used here, that we assumed here is constant. So we are not changing this model. This is not for the proof of stake things. but it could be explored there as well. Yeah. It could be. It's a good idea.
So is there any guidance for how to choose C, or is it
No,
just,
because these protocols are being abandoned anyway. I have to say the Ghost protocol has not been popular. The longest chain is there, but it is complemented by other means like finality gadgets or things like this. So these protocols are not in that pure form existing anymore. And remember, I put this under proof of work, and all of proof of work, in my opinion, should be deprecated anyway. Except the Bitcoin will not deprecate it, I'm pretty sure. But many other places are abandoning that, yeah. Yeah, and there's one more thing, but I'm only going to mention here the result. Yes?
So the Ghost you put under proof of work model,
I have put it on the proof of work, right?
the medium is also under.
This is also the same, right? That there's pure mining power that comes in here. These blocks are mined with a rate that is about like the mining rate in a pure mining power, yeah. This is not about, we didn't do any analysis for stake-based protocols or something like that. Yeah. This is only
long range.
in that sense. There is no long-range attack because we cannot go back and expose keys here, right? But if you would transport these ideas into the proof of stake world, then there might be. So we have to look at it again. And I don't think it helps a lot against the long-range attacks. It will not help much. Yeah. Okay. Well, last but not least, there is also the question. Now we've seen all these resources, right? Work, storage space, time weighted, and so. And this is one work that we did with Duc van Leer, who is also here, where we used an abstract resource allocator to give us permission to use the resource for creating a block. And then we can create not exactly the same protocol, but a family of protocols that we can see how they behave with this abstract notion of resource. So the question is, what is actually the resource, the voting power here? And it's an abstract notion that we can characterize through a resource allocator where we can go to and ask for some resource if we have certain power, or we're given this, and then we can construct a protocol that works from this abstract resource. Yeah. So the question is, what kind of features must such a resource have? Yeah. And I'm not giving you the answers here for this. Well, it must be able to commit to it. And the question is also whether or not there is an ample supply of this outside or not. Yeah. But that's another work we looked at. And that's also where I wanted to close now for the moment and be open for more questions. And yeah, thank you for attending.